All right, guys, so we're going to go ahead and talk about how to write these exponential functions today. We already have looked at the fact that there are growth functions and decay functions. If it is a growth function, remember that it's going to be going up exponentially, so it looks kind of like that on the coordinate plane. And if it's a decay function, it starts up and then it goes down, so it kind of goes down on the coordinate plane. So when we're looking at these, we have two different formulas to look at. The only difference between the growth is that inside of the parentheses we have add, and decay inside the parentheses we subtract. That's the only difference between those two formulas. So we will, if we identify that it's a growth function, we'll add the rate plus 1. If it's a decay, we will subtract it. So let's take a look at the individual pieces here of the function. So we have A, our initial amount, and those are going to be our y-intercepts. So this will be where it crosses the y-axis, or where we started. We have our growth factors, and in each of our growth factors, you guys will see the R. When you see the R, that's the rate as a decimal. So we're going to convert the percent to decimal for both of those. And then time is always going to be in years. So those are the different pieces of our functions. We're going to practice writing a growth function and a decay function. So to start off, we're going to look at this first example for growth functions. It says the population in a town is currently 8,250. That would be our initial amount, A. It has been increasing 3% each year. That 3% is our rate, so we're going to convert that to a decimal, 0.03. And they want to know what the population will be in 10 years. And that 10 is our T time. So from there, all we have to do is use our formula. Y is equal to A, our initial amount is 8,250. Parentheses 1 plus our rate is 0.03. And to the t power, which is 10 in this function, 10 years. Then we're going to take that function and we will plug it into the calculator. And when we plug that function into the calculator, we should get about 11,087 people. And that should make sense. It is a growth function, and 11,000 and some change is definitely bigger than 8,000. So it should make sense that that is a reasonable answer. For the decay function, like I said, the only difference is that we are going to subtract because it is decreasing over time. So our first example here says Yasser bought a car in 2012 for $16,000. That is going to be our starting amount, our y-intercept. The car's value has been decreasing. That's telling us it is a decay function, that it's decreasing at a rate of 7% each year. That 7% is going to be 0.07 as a decimal, and that's going to be our R in our function. And then they want to know how much was the car worth in 2018. So to find our time in years that has passed by, we're going to have to see how far apart 2018 was from 2012. And when we do that subtraction, they are 6 years apart. So that is our time that has passed in years. So now we have all of our different pieces. Just like before, we're going to go ahead and plug those in. We have Y is equal to A, our initial amount was $16,000, times 1 minus, because it's decay, the rate, which is 0.07, to the t power, which is 6 years. Then, just like before, we're going to plug that into our calculator, and when we do that, we should get about 10,351.84. You might get a longer decimal. Just remember that with money, you always round to the hundredths place. So those are our growth and decay. Like I said before a couple times, the only difference is for growth, you add, and for decay, you subtract. We have a special kind of exponential function to look at as our last formula, and that is for compound interest. When we're talking about compound interest, it means that you've either borrowed money or you have a loan, like if you bought a car or a house. And if it's compounded, that means that the rate at which you are owing money is increasing over time. So the longer you take to pay something off, the more money you are owing them. So our formula here has some similar pieces. We've got P principal. That is going to be your starting amount. Principal would be what I am borrowing from somebody. And then we have rate, just like before. We're going to convert that to a decimal. It's going to be given to you as a percent. Number of time periods. This is where this is a little bit different. If I am compounding the interest, that means every time a time period goes by, how often it's compounded, I owe more money. So we've got some helpful hints here for what N could be represented by. If they say that it is annually, that means that it happened once a year that it was compounded. If it happened semi-annually, it was compounded twice. Quarterly, it was compounded 4 times. Monthly, there's 12 months in a year, so 12 times. Weekly, 52, because there's 52 weeks in a year, and daily would be 365, because there's 365 days in a year. And then finally, we have our time still in years. So a little bit more involved to this formula, but still the same process. So we're going to read our first example. It says a savings account has a fixed annual interest rate of 3%. As a decimal, we're going to convert that to 0.03. It is compounded semi-annually. If it's semi-annually, that means it happened twice. It was compounded twice, so our N value is 2. If Paul invests $5,000, that's his original amount, so that would be our principal, P. And then it happened for 6 years. How much will he have after 6 years? So that would be our time, T. So just like before, we're going to plug into our formula. This one looks a little bit different. So we've got A is equal to P, the principal, which was 5,000, times 1 plus the rate divided by the N. So the rate was 0.03 divided by N, which was 2. And then our exponent is going to be the N value times the years. So our N value was 2. The years was 6. So when we plug that into our calculator, we're going to plug it in as 5,000 times 1 plus 0.03 over 2 to the 12th power. And I'm running out of a little room, so we're going to come over here and plug that into our calculator. When we plug that in, we should get about 5,978.09. So that would be how much he has after 6 years.